Welcome to this lecture in the course on convex optimization. So today we shall look at a very popular algorithm for convex optimization called steepest descent method. Um, s- uh, in steepest descent method, we shall look at the algorithm itself in the first place, then convergence properties of the steepest descent method, and then we shall look at uh, a very important topic on rate of convergence. So how do we define the rate of convergence of an algorithm? This is which is very important for uh, analyzing algorithms and especially comparing them. um, so let's start now. So let f be a convex function. F is convex. So f of x plus v. So this can be approximated like using first order Taylor's approximation as see f cap f hat x plus v is equals to fx plus gradient of fx v. So this is basically the first order Taylor's approximation. So note that this term here, the gradient of fx, gradient of f transpose v, this is called a directional derivative of f at x in the direction v. So basically this gradient of f, like this is being projected towards along like v. So this is directional derivative um, along v in the direction of v. um, we know that a sufficient condition for this v to be a decent direction is that this gradient of fx transpose v should be negative. To understand this, so we have any, so let's say this is contour plot. So because sublevel sets are con um, vex for a convex function, so the contour plot is something like this. And so let's say this is x, then uh, the gradient will be in this direction, right? So if v is descent direction, then so from x this v, so if v is y minus x, then y has to um, lie on this side of this line, right? So y has to be somewhere like this. So this will make a angle greater than 90 degree with this gradient of f at point x, and hence this equation has to be satisfied. So this is a necessary and sufficient condition. I mean this is a, yeah, I mean sufficient condition for um, v to be a decent direction. Um, so steepest descent direction is so this is a decent direction. So this is a condition for decent direction. And what is the steepest descent direction? So it is the direction along which the yeah, like the rate of decrease of f is maximum. Basically this is given as um, so let's say this is, let's call this h. H is the steepest descent direction. So this is argmin um, with respect to v. um, yeah, this gradient of fx transpose v such that this norm of v is less than equals to 1. So basically this is the general definition of um, steepest descent direction. Now this norm can be I mean, it can be like any norm. This can be a quadratic norm, L1 norm, infinity norm, like that. So for different norm, we get different directions uh, for steepest descent. And so we saw this in the lecture in the last Wednesday class. So we saw that for L1 norm we get uh, we get what you say, this coordinate descent. So this is minus sine of, we saw this uh, del fx by del xi into ei. So ei is vector where ith coordinate is 1, rest are 0. So what is I is the index um, of that index of that coordinate of gradient of fx, for which has like maximum value. Similarly, I mean, we had same answer for, sorry, um, L infinity norm. Yeah. Interestingly, we had for Euclidean norm. For Euclidean norm, we had minus of gradient of fx. So this was the steepest descent direction for Euclidean norm. So uh, so I mean, we saw all this during last Wednesday lecture. Um, so for today's discussion, we will take this example. I mean, descent, we will consider Euclidean norm and descent direction to be minus gradient of fx. So now uh, yeah. So in steepest descent method, so what we do is, so first we find a descent direction, let's say h. So the first duty is, so we have x, so we have f, we have xk. Then at this xk, for this f, we find the descent direction. Descent direction is minus h is equal to minus gradient of f of xk. Having found this, then we find, so then we actually we update x, we find xk plus 1 using this xk minus t times h is here. I mean, this is minus is also from h only. Yeah. So this is how we update x actually. Um, so first we find so we have xk, we find a descent direction, then we want to find new x using that descent direction. um, so 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 this is basically t times h. Yeah. So now, but we also want step size is t. uh, so because if we have something like that, and if we don't take step size carefully, so even though this is a descent direction, if we take step size to be very large, we may not land at a smaller value. So I mean, we want f of xk plus 1 to be less than f of xk, right? So to find t, we basically so there is one uh, obvious choice, is that to uh, minimize f. So to consider this function f of xk minus t gradient of f of xk, and minimize it with respect to t. However, this is at times this is difficult. So a popular uh, iterative algorithm is using backtracking. This is called, I mean, direct optimizing this with respect to t is called exact method, and the other method is backtracking. In backtracking, um, backtracking is a iterative method. So in backtracking we choose two parameters. One is alpha, which is between 0 and um, half, and beta, which belongs to the open interval 0 1. And so in backtracking we choose initially t is equals to um, let's call this t0 is equals to 1, and we compute the value of this term, right? And if this is greater than f of xk, we decrease t by beta. So t1 is equals to beta t0, and similarly we keep on going until uh, the backtracking exit condition, as this is called, is satisfied. So what is that? So this condition is that so f tilde t. So f tilde t is basically um, this, we are the same function where we consider this as a function of t. This is less than equals to I mean, this is less than equals to f of x minus alpha times gradient of um, f x, sorry, uh, so this square. So until this is satisfied we keep on reducing t, um, right? So this is backtracking. Now we are guaranteed to actually satisfy this because because uh, because this h is a decent direction. So I mean, there's certainly, if you move in this direction, I mean there's certainly some at some point in this direction for which f of like x k plus 1, xk of k plus 1 is the entire um, uh, this term inside this function, that is xk minus t of gradient of t times gradient of f of xk. So this will be less than f of xk. I mean, we are sure to find such an x of k plus 1. So ultimately this will be satisfied. um, so we saw that initially we find a decent direction, then we uh, find t using backtracking uh, method, and then we use that to find x of k plus 1, right? And then we keep continuing this process until some stopping criteria is satisfied. And when the last, so let's say when we have when k is equals to t, k is equals to capital T, so when k is equals to capital T, and this stopping criteria is satisfied, then we finally return x of t as the optimal solution, optimizer. I mean, because we are considering minimization process, so x of capital T is the minimizer, and f of t, f of x superscript t, I mean this is the optimal, I mean the minimum value. So what is the stopping criteria? So I mean there are different uh, criteria that are used in practice. So for example, stopping criteria. So for example, one can take, so when the gradient of f is very small at xk, so epsilon is a predetermined value. So if this is small, we say that okay, we are done, so we return x subscript k as the minimizer. Or what we can do is we can just see that the decrease in the value of the function is not enough. So this will tell us that we are close to uh, the optimal value. Similarly, we can also look at the, so I mean it depends. So if we want uh, the, if the problem is arg min or min, I mean, so what we can do is we can also choose this as the stopping criteria. So x of k plus 1 minus xk is less than epsilon. So this can also be a stopping criteria. So this depends. For example, if the function is somewhere like this, so this is, or sorry, so if a function is like this, so this is xk, this is um, sorry, yeah, or let's mm, mm, yeah, so if, so consider this example. So now, so the difference in value, so let's say this is xk, this is xk plus 1. So this is very large actually, but the difference in uh, f of xk and f of, yeah, so I mean, yeah, I mean to say that the difference in the value of the function may decrease by very less, but the actual minimizer might still be very far away, right? um, while on the other hand we can have a function where, so the minimizers, yeah, so things might be, the function might be dropping very sharply, and but the points, the x values might not be changing very fast. Yeah, so I mean, so there are different criteria that are used. So each time we compute new x value of x, that is xk plus 1, we check this stopping criteria. If it's not satisfied, then we again find a descent direction at xk plus 1, and then find the step size t, and using backtracking method, and then we find xk plus 2, and again check the stopping criteria. So this goes on until the stopping criteria is satisfied. Now we will briefly look at the trajectory of steepest descent method. So for now, like, let's say, so if exact line search is followed, so backtracking is like more numerical. So if, let's say, exact line search is followed, then so you can have some function like this. So this is contour plot. So at this point, you find the descent direction. So this is your xk, you find a descent direction and you move in that direction. So you are using exact line search. So you find this point. At this point, now you find the descent direction. So you find the descent direction. Now you find, yeah, again use exact method to find step size. So you find something like this. Now again you find descent direction, and you keep on going like this. So this is xk, this is xk plus 1, this point is x of k plus 2, and like that. So one interesting property here is that, okay, So let's define this psi of t is equals to, I mean, we will come to that property. So I mean, intuitively we can see that it seems that yeah, so this line, like x of k plus 1 minus xk, I mean this line is perpendicular to um, x of k plus 2 minus x of k plus 1. I mean this looks to us. So we will actually find that this, if we use exact line search, I mean this is actually true. For that, we consider this function psi of t is equals to f of xk minus t gradient of f of xk. If we differentiate it with respect to t, we get f prime xk is t gradient of f of xk and times minus of gradient of f of xk, right? But what we do in exact line search, in exact line search we are basically minimize this psi of t with respect to t by differentiating it and equating to 0. So the result of the exact line search is the t for which this is 0, right? um, so what this means, so this, so now what this means, that this is 0 and this first term here is basically f prime x of k plus 1 x of k plus 1 for t, for t for which this is 0 now. So into gradient of f of xk, basically this is also gradient of minus is equals to 0. So basically this is perpendicular to, I mean, the dot product is 0, so these two are orthogonal. And so from here we see, so this is the direction of f of xk, gradient of f of xk. This is the direction of f of xk plus 1, so these are perpendicular. So now we will briefly discuss analyze the convergence properties of uh, gradient descent, steepest descent method. So convergence analysis. So let's consider this m smoothness property. So we will assume that x less than equals to, this is conic, conic generalized inequality. Yeah, this is I, and we also assume that yeah, so we will assume these two. Yeah. So from first, it follows that f of x plus tv is less than equals to f of x plus t times gradient of f of x transpose v plus m by 2 norm of v t square. So for now we consider this, we are denoting the steepest descent direction with v, so this is gradient of f of x basically minus, yeah, equals to, I mean substituting v is equals to this value, I mean we get f of x minus t times norm of gradient of f of x square plus m by 2 t square gradient of f of x square. I mean this is all 2 norm. Now so if you minimize this with respect to t, we find that t is equals to 1 over capital M. This actually satisfies um, I mean minimizes this side. So I mean if we substitute it, I mean the direction of the inequality will still hold. F of x plus tv is less than equals to fx minus 1 over m into this gradient of f x square plus m by 2 into 1 over m square to gradient of gradient of fx square. And this is equals to fx minus 1 over 2m to gradient of f of x square, I mean norm square. So I mean just compare this to this function f of x minus alpha times 1 over m and gradient of f of x square. This 1 over m is t basically. Yeah, so for alpha less than half, certainly this is I mean this last expression is greater. So this is exactly the backtracking exit condition. So so yeah, I mean f of x plus t v, I mean this has to be less than f of x plus alpha times t in plus alpha times t into gradient of f of x transpose v. So basically we can write this as gradient of fx transpose v and minus sign from here, like this will cancel this minus sign. Yeah, so I mean so this is the exit, like backtracking exit condition. So the algorithm will, I mean so certainly for t is equals to 1 by m, this exit condition is satisfied. So t, so what happens basically, t, I mean the algorithm starts with backtracking algorithm method starts with t is equals to 1 and keeps on decreasing it with factor beta, right? So how less it can go, it has to be like for t less than equals to 1 by m, this condition will be satisfied, right? So how, what is the smallest that it can go? So it can go like at most beta by m, it can go by beta by m. So in one step it can be just slightly greater than 1 by m, and so we multiply it with beta, and next step it will be beta by m. So t is greater than equals to beta by m, I mean minimum of beta by m. So what if yeah, what if beta I mean uh, yeah, because it starts with 1, it starts with 1. So what if beta by m is greater than 1? So in that case it will give 1. So t is basically greater than equals to min of 1 comma beta by m, right? um, okay, so f of x plus, so let's say we have x and x plus is the next step. So basically x plus is equals to x um, x plus th, right? I mean tv, where v is steepest descent direction. So this f of x plus is equals to f of x minus alpha times min of, I mean sorry, this is less than equals to alpha times min of I mean this is basically the t, like this is what we are writing. So t min of 1 comma by m, so into norm of gradient of f of x square. So so I mean this is the same equation here, where we have substituted t is equals to min of 1 comma beta by m. Fine. Now so subtracting p star, let's say optimal answer is p star, and we are looking for basically p star. So subtracting p star from both sides, we get minus p star is less than equals to fx minus p star minus alpha times min of 1 comma beta by m to norm of gradient of fx square, right? I mean all these norms are 2 norms. From strong from strong convexity, I mean we assume to start with that mi, this is then f of x, I mean this is as a direct consequence of this, we have as a direct consequence of this we have p star is greater than equals to fx minus 1 by 2 small m gradient of fx square, right? So from here we get gradient of square is is less than equals to p star minus fx times 2m, right? So we get this. Now we substitute this in this expression, and we get f of x plus minus p star is less than equals to f of x minus p star plus alpha times min of minus f of x plus p star 2m. So basically what we have done is we have substituted this term with this term. in the previous equation. And just simplifying this, we get f of x plus minus p star is less than equals to f of x minus p star. I mean, we take this common, we get this times 1 minus alpha times 2m into min of 1 comma beta by m, right? We get this. Now so we have this, we call this term as c. So this is c times f of x minus p star. So similarly, so this is from one step, this is for one step. So if we go up to x of k minus p star, this is less than c to the power k into f of x minus p star, right? So how we got this? So basically, so we have this less than equals to this term, and here we again replace this with, say, previous of it, and we keep on going like this. So this is less than equals to again c times f of x minus p star, like that. So yeah, so from there we get this expression, right? Now note that this is called linear convergence. I mean, this is linear convergence. I will just discuss about rate of convergence. So this is called linear convergence. So steepest descent method has linear convergence. Okay, so next I will discuss little bit about rate of convergence. So if we have a sequence, first let's define an error function. So error function e of k is equals to f of x of k minus p star. P star is your okay, or now let me, okay, okay, so leave it p star. So let's call this is as the error function, and to define, we define rate of convergence as the rate with which this e to the power, I mean this ek, this sequence ek decreases. Is for that we compare this sequence with another standard sequence, say rk. So I mean, this k is not power, this is just a superscript. Yeah. With so we compare this with another standard sequence rk, and ek and so both ek and rk are positive, and as k tends to infinity, this ek tends to 0 and rk tends to 0. So ek convergence is slower than rk. So ek is said to converge slower than rk if there exists k bar greater than 0 such that rk is smaller than equals to rk is smaller than equals to smaller than less than equals to ek for all k greater than equals to k bar. So if this is true, then you see this error is greater, so that means error is like the sequence is converging slowly towards 0. So basically ek and rk both are converging to 0, so ek is slowly converging slowly to 0. That means this fxk is converging to p star slowly. So it's like this is slower convergence. And if we have ek less than equals to rk for all k greater than k bar, I mean in that case we will call this to have ek to be converging faster. So the convergence of f of xk, I mean, is faster towards p star compared to rk. Now what is linear convergence? So for that we consider this popular sequence. I mean this is so q beta to the power let's say ak yeah. So we compare ek. Now let's keep k here in subscript, because here this k is in power. So in ek let's keep this in subscript. Yeah, so we compare ek with this sequence. So b to the power ak. Yeah. If so this is our rk, this is basically our rk. So here beta is called convergence ratio, and a is the order of convergence, and k is the index of the iteration. Yeah, and q is, this is some q greater than 0. So q is greater than 0, beta belongs to 0 to 1. I mean this beta is different from the beta that we just discussed for backtracking. I mean forget this backtracking thing. So this is all new notation. So this q is greater than 0, beta is between 0 and 1, and k is the iteration, and this a is the order of convergence. So let's say a is equals to 1. So if a is equals to 1, then we are comparing this ek to first order, I mean linear convergence. So so I will now so if a is equals to 1, so if a is equals to 1, then we are comparing ek to q beta power k. Then we say ek to converge at least linearly with convergence ratio beta star. So ek convergence at least linearly with convergence ratio beta star if it converges faster than all geometric sequence. I mean this is geometric sequence. So this, if this converges faster than all geometric sequences of form q beta to the power k, where like q is greater than 0 and beta is interval beta star to 1, there exists k bar such that ek is less than equals to q beta star to the power k for all k greater than k bar. So this ek is said to converge at least linearly if at least linearly with convergence ratio beta star if for all beta greater than beta star and less than 1 there exists some k bar such that this ek is less than equals to q beta star to the power k. Similarly we say that it converges at most linearly with so this is at least linearly, and we say that this convergence at most linearly with convergence ratio beta star if there exists, so this is at least linear convergence, and now we are discussing at most linear convergence if there exists kq bar such that for all q 0 this is eq is greater than equal to this for all k greater than kq bar. So if this happens, then there is at most linear convergence. Now we call ek to converge linearly with convergence ratio beta star if there exists. Now this was at least at most. Now this is linear convergence. So this is linear convergence if there exists kq bar such that ek is equals to q beta star k for all k greater than equals to kq bar. So linear convergence if there exists kq bar such that ek is equals to q beta star k. Yeah. So now we return to our discussion here. So this is what? This is ek. This is ek. And this is less than equals to, so you can call fx minus p star as q, call this as q. And so on left hand side we have ek, on right hand side we have this q, and this c is basically beta, c to the power k is beta to the power k. So this is why this is a linear convergence. Yeah, I mean this is important. So so for now, I mean just ignore this at least and at most definition. So linear convergence, so if this ek is equals to q beta to the power beta star to the power k for all k greater than equals to kq bar, then this is linear convergence. Similarly, this there is called super linearly. I mean convergence is super linearly if it converges faster than every sequence of form q beta to the power k. I mean, so we had for at least, so at least we had that convergence is faster than for beta greater than beta star. If it is for all beta in interval 0 to, this is called super linearly convergence. And we call sublinear if convergence is slower than every sequence of form q beta to the power k. If convergence is faster than all q beta to the power k for all beta in interval 0 1, this is super linear convergence. And if it is less than for all beta, I mean then it is sublinear convergence. So now we will quickly look at a couple of sample problems that comes in this field. I mean from this. So let's say we have like some algorithm converges linearly with convergence ratio beta star. So if we are given that for some algorithm the convergence ratio is beta star and the algorithm converges linearly, then find the number of iterations, number of iterations required to ensure that error never exceeds epsilon, such that ek is less than epsilon. So to solve this, so we know that e to the ek is equals to q beta star to the power k, and this has to be less than epsilon. And we want this k, right? So basically beta start k is less than epsilon by q, so we take log, so k into log of beta star is less than log of epsilon by q. This implies that k is greater than log of q over epsilon. So I mean the sign has reversed here because we have actually reversed this. Yeah, right. This is log of beta start. So we have a lower bound on k. So this is yeah. I mean, for k tending to infinity, I mean this has to go below epsilon. Yeah, right. Um, Similarly, we can have another example. Um, so let's say ek is equals to 1 over k. So find the rate of convergence. Find rate of convergence. Let q is equals to 1 and beta. I mean some beta belongs to 0 to 1. So I mean for we only have to show that for there exists some q and some beta. I mean if you want to show linear convergence, so we just need to show that there exists some q and some beta such that ek is equals to q into beta to the power k, right? um, but we can yeah, now like consider this ratio. So q is equals to 1 and here we just consider that there's some beta in this interval and we take this ratio, right? So this is basically substituting q is equals to 1, this is basically k into beta to the power k. So as k tends to infinity, this tends to 0 because beta is between 0 and 1. We know that, so we can say that this q beta to the power k is equals to small o of 1 over k, right? This says that I mean what this means, this means that 1 over k decreases much slow, like 1 over k decreases um, q beta to the power k decreases much faster than 1 over k. So that is why I mean this decreases much fast from this, that is why the ratio tends to 0. So that means 1 by k decreases slower than q beta to the power k, so the convergence is for all beta. So here what we have shown is that this 1 over k converges slowly to 0 than q into beta to the power k for all beta in interval 0 1. This is sublinear convergence. Sublinear convergence, right? So yeah, so this is one example. Similarly we can show it for many different um, like error sequences. For now I will just conclude. Uh, so this is it for today's lecture, so thank you.